So we're looking at higher derivatives. Can you guys see my screen?
Yeah.
Yes.
Right. So I suppose you guys would have seen or spoken about higher derivatives, eh? Like, what does a higher derivative suggest to you? That's the first derivative. So a higher derivative is just when you differentiate that again. Okay, and so you could just keep differentiating these functions if you needed to find the second and the third derivatives. There's the second, there's the third. So the important thing you need to know, really, because it's the same process, you just need to know about the notation. So if I've got a function of x, I differentiate it, I get f dash x. If I differentiate it a second time, I'm going to get f dash dash x. We're happy with that?
Yeah.
If I've got y and I differentiate y, I get dy by dx. Yeah. If I differentiate again, I differentiate y with respect to x again. So I get d squared y over dx squared. It's because how I view it is this d means I'm differentiating. So that means I'm differentiating for the second time with respect to x a second time. Does that make sense?
Yeah.
So the third derivative would be d cubed y over dx cubed. Happy with that?
Yeah. Would we have to write that down, or could we just stick to like the multiple lines over the top?
If you do f dash dash, that should be fine, yeah.
All right, sweet.
Okay. But so here, if I differentiate y, that's a simple 15x to the power of 4 plus 8x plus 7 plus 2e to the 2x. You guys happy with that?
Yeah. Yeah.
When I differentiate that a second time, what do I get? I get
60.
Yep. X to the power of
X cubed.
3. Yep. Plus
8.
Plus 4e to the 2x. Happy with that?
Yep.
And so if I differentiate a third time, I'm just going to get 180x squared plus 8e to the 2x. In that process, I can carry on going if I needed to, if you guys could imagine that. Any questions there?
No, that's all good.
So the only thing really is to make sure you know about the notation. So f dash x, differentiate sine 2x, I get 2 cos 2x, don't I? Question? If I differentiate sine 2x, do I get 2 cos 2x?
Yeah, because use the chain rule, right? I haven't really practiced the trig ones too much.
Yeah. Well, make sure you have a little go at the trig ones. Because yes, but you do use the chain rule. And then differentiate that 2x. And then when I differentiate that a second time, that becomes negative 4 sine 2x, I believe. And then this here is now a product. So you write down the first, differentiate the second, plus write down the second times the differential of the first. And then this is where it starts to get a little bit trickier. Okay, but I mean, it's just to find the third one, all I got to do is do the product rule there. Is that a product? This last one, is that a product?
I'm not sure. No.
No, because the 2 is in a function of x. Here,
Oh, yeah.
2x is a function of x, and e to the x is a function of x. So there's your 2 functions. But 2 is not a function of x, it's just a constant. Does that make sense?
Yeah. That's perfect.
Okay. And I suppose where we need to know and where the second derivative is actually helpful is the second derivative helps us find any points of inflection, okay, which are important, because from there we can figure out if our graph is concave up or concave down. If a graph is concave up, then it is like a bowl. That makes sense. And because it's a concave up graph, because it's a bowl, what is the turning point that is housed within a concave up? That is a minimum turning point. Does that make sense?
Yeah. So you
Yeah,
just
this-
like, if you just use that in like ones where you're trying to find turning points, pretty much, just like with the. So it's just a faster way to do that instead of like substituting in values.
Yeah, well, yeah, exactly. Like if I give you an x cubed graph, you probably know the shape of that. And you know the first one was the maximum, the second one was the minimum. But if I give you a x e to the x graph, you're like, oh, that isn't right. X e to the x is like, well, what does that graph look like? Where is it a max, where is it a minimum? This is where you're going to use this second derivative stuff. Okay. I suppose the key thing you need to remember is concave up is when the second derivative is positive. Concave up is a bowl, which gives a minimum turning point. Concave down is your N-shaped graph, and it gives you a maximum. Up is your U, down is your N. Minimum for concave up and maximum concave down. So there's your little overview. The first derivative tells us turning points where the function is increasing and decreasing. How do you know where it's a turning point? F dash x is equal to
0.
Where do you know the function is increasing?
When that is positive.
It's greater than 0, and it's decreasing is when it's less than 0, yeah?
Yeah.
So the point of inflection is where your second derivative is 0. Concave up is when your second derivative is positive. Concave down, your second derivative is less than 0. And this is basically telling you where your graph is a U or an N. It's like this is like your umbrella where sort of rain falls off. And this is like your bowl where your rainwater is collected, if that makes sense. So any graph that you think, oh yeah, that graph looks like it collects water, that is a concave up function. Concave down is your umbrella type one, and that's where your second derivative is less than 0. The main point you use is when you will differentiate a second time shortly to prove whether there is maximum or minimum. Okay, and I think there's another video for that, but hopefully that makes sense. Are there any questions with that stuff? George, you've just joined it. Any questions?
No.
Okay, well, I'll stop the video there.